Good afternoon, ladies and gentlemen. My name is Lubomir Říha, and I'm gonna present you how we can tune the HPC application to save some energy. So the overview of my talk is as follows. I will show you the methodology, the motivation and the introduction, how the methodology has where the methodology was developed, that was within the READEX project, what is the dynamic tuning, and how you can achieve the energy savings. Then we will talk about how tuning of the hardware parameters have effect of energy consumptions on today's HPC hardware. Then I will show you as one of the key parameters that will be discussed today is arithmetic intensity, how different tuning and what are the different optimal settings if you have applications with a different arithmetic intensity, and how one should set the hardware parameters to optimize for energy. And so this will be pretty much like the basics, showing how the idea works on elementary kernels, and then we will see how the methodology can be applied to a complex HPC application. We will show we will focus on three of them, which one is BEM4i, the other one is OpenFOAM, and then the one is the ESPRESO, which is the finite element method. We will also talk about the potential that we can even help you to find the optimal settings using the tuning the application parameters, and that's gonna be shown towards the end of my talk. So let's start with the READEX project and what was actually the motivation of the READEX project to start this kind of a research. So the READEX project has been a Horizon 2020 project that's been successfully defended at the end of 2019. The idea of the project is pretty much shown on this very figure. As your application is pretty much executing from one phase to another, you can have a different phases. For instance, if you have a finite element method to method solver, then you need to assemble matrices, then you have to run a linear solver, then you have to do a post-processing, then you have to save the data to the hard drive. Those are different phases of the application, and each of these phases requires different settings and utilize different resources of your system. So as your application progresses, their characteristics, computation characteristic and requirement changes, and you can tune your hardware to always give that particular resource what it needs to run as fast as possible, or potentially to minimize the energy consumption. So this on the right side, these are the partners that has been within the READEX project, and let's talk about the idea of the dynamic tuning. So the dynamic tuning pretty much means that as your application progresses from one phase to another, you call these phases, we call them region. In here, the significant region. This was the methodology used in the project. And as you go from one significant region to another significant region, you pretty much tune the hardware for that particular region. So what you need to do is you have to know what are the optimal settings for that particular region, and you have to have a runtime system that pretty much applies those settings as your application switches from region to region. So in this simple case, we have a loop that has two functions, which is Laplace 3D and FFTW execute. And let's say we just tune the core frequency, the frequency of the CPU. So in this case, the Laplace, the optimal frequency would be 2 GHz, and the FFTW execute will be the optimal frequency would be 1.2 GHz. And then as your loop progresses, then it will be based on entering these two regions. The runtime will just keep switching the frequency of the CPU between 1.5 and 2 gigahertz. So this is what we mean by dynamic tuning in the context of this talk. So the whole READEX methodology has been actually implemented into a READEX tool suite. The idea of the tool suite is pretty much to execute these 4 steps, where the first step is to instrument the application, which means you have to find the significant regions. We define the region as a region that is long enough, which means in the project it was determined that the region has to be at least 100 milliseconds. Then you have to detect the dynamism. It means that you have to find the optimal settings for each of the regions and compare what savings you can achieve. Then this was actually also part of the step 3. And then if you find the optimal settings, you just have a production runs, which is step 4, and within the production runs you apply the optimal configurations. And this is your this is the end of the analysis. You have your optimal settings, and you always run the application with the runtime that performs the tuning. In addition to the tool suite, which actually performs the tuning and implements the whole methodology, there's also developed a test suite, which is a set of benchmarks that you see in a table on the right. And this was actually a validation tool for the methodology, and all the results that most of the results that I'm gonna be showing are used from results measured within this test suite. So you can see that it has several benchmark or proxy apps like AMG, BlastBench, Kirki-Roulage, NASPARAL benchmark, but also for production applications like MEMFORI, ESPRESO, Indeed, and OpenFOAM. So this is some of the results that I'm going to be showing in the next slides. So yeah, I guess we can move forward. So this is a first set of results that I want to show you, and it is what you can achieve if you do a static tuning. So by static tuning, we mean that you have an application and then you find the optimal setting for an average run of your application. So it means you don't have any regions, you just find the optimal settings for the entire runtime of your application. You don't try to optimize in the regions, but just the whole application on average. So this is what we call a static tuning. So for the READEX test suite, we were able to achieve approximately 12% of energy savings just to performing the static tuning. And then if we go one slide further, then here we have the dynamic tuning. And on average, we were able to achieve up to almost 18%. But some of the applications really have significant savings. Like I'm going to show these towards the end of my talk. But for instance, the MEMFORI application has up to 34% of energy savings. So this is pretty much. This should give you the idea what one can expect when perform the dynamic tuning to save the energy. This would be probably the range that you can expect also on your application. If we go a little bit into the detail, what the methodology can provide, I mean, you see that at this point, in this slide, we show again the difference from the static and dynamic tuning. We show it per each of the applications from the READEX tool suite. but this slide also shows what we tune. So in the hardware parameters, you see that we tune the CF, which is the core frequency. We tune the UCF, which is the uncore frequency. The uncore region of the processor is pretty much everything that's from level 2 cache up. Not level 2 cache is not included. So level 3, the last level cache, the QPI, the memory controller. So everything that's pretty much is a memory bound is affected by this uncore frequency. Anything that is a compute bound is affected by the core frequency. And then we tune the number of threads using the OpenMP number of threads. So if you take a look at the static tuning and the dynamic tuning, you can see that the first set of numbers is the energy savings, and the second after the backslash, it's a negative values, which is the time. So what this means that usually if you go and you just maximize the energy savings, you usually pay with the runtime. In some applications you pay more with your runtime, in some applications you pay less. But this is just the optimization objective that you have. In this case, the optimization objective was set to just minimize the energy as much as possible. If you can set a different criteria, you can minimize the energy under the specification that you don't want to lose more than 5% on your runtime, and then you can get different values. Just this is possible. It's just a different criteria for the optimization. But also, I would like to show that some of the applications, in this case, the BEM4i, also you see that we also saved in the runtime. The runtime was the savings in runtime was positive number as well. So this is these are another aspect of the energy of the maximizing the energy efficiency. Usually, what happens that there is some penalty that has to be paid by the runtime. But as I said, it's a matter of optimization goal, and that gives you pretty much a little bit less energy savings if you don't want to sacrifice the runtime. So, okay, so I give you pretty much the main idea. I give you the what can one save on a complex applications, and now I would like to talk a little bit how actually these savings are achieved. So let's focus first on tuning of the hardware parameters. So in these slides, we show how the stream benchmark, which is pretty much just a benchmark that tests the memory bandwidth, and in a sense it's a pure compute bound benchmark, how it is affected by uncore frequency. So on the left figure, we see how the bandwidth, how the performance of the memory subsystem is affected by changing the uncore frequency, going from 1.2 to 3 gigahertz on this. This is a Haswell processor, Intel Haswell processor. So you see that going from 1.2 gigahertz up to 2 gigahertz, pretty much you see that you're gaining a lot of performance, but increasing the frequency. But after that, going from 2.1 to 3 gigahertz, the performance is increased a little bit, but not as significantly as up to this point. On the other hand, if you look on the right side, you see that the average power consumptions just grows linearly. And putting these two together, you see that there is a sweet spot on approximately 2.1 gigahertz that just tells you, okay, this is the optimal settings for me in terms of the energy consumptions. And if you look at the graph on the left, you see that yes, I'm not getting the full performance on 2.1 gigahertz, but from energy point of view, this is my optimal point. If we take this a little bit further, this is again a stream benchmark, but right now this shows the results from both tuning the uncore as well as the core frequency. So on the left, pretty much you will see this is the performance, and you see that changing the core frequency does not affect the performance at all. Changing the core frequency from 1.2 on the default configuration from 1.2 to going to 2.5, which is the maximum frequency of this processor without the turbo, doesn't affect the bandwidth. The bandwidth is still 77 gigabytes per second. But you see that on the horizontal axis, changing the uncore frequency from 1.2 to 3 gigahertz, that is what makes the difference. So this is just the performance. If you look on the right side on the graph, you see that still increasing the core frequency increases the power consumption. So the optimal is keeping the core frequency as low as possible, in this case 1.2 gigahertz, and just use the optimal frequency, uncore frequency, which was the 2.1 gigahertz, and we are in this range where the optimal settings are. So this is this was the stream benchmark. And it pretty much reads the data from the memory, from the DRAM. On the other hand, if you run the stream benchmark that has the data in the level 3 cache, you see here that the performance is affected by both core and the uncore frequency. So in this case, it's not optimal to just use the minimum core frequency, because your data can get to the CPU faster. It needs to run a little bit faster to be able to process the data, and your sweet spot in terms of energy is somewhere in the area of 2.1 gigahertz uncore frequency, and let's say 1.6, 1.7 gigahertz of a core frequency. So for this particular workload, the optimal settings have changed. So right now I'm going to show you how actually, so this is how the arithmetic intensity changes the behavior of the processor, and more particularly, what are the optimal settings for different arithmetic intensity. So we have a benchmark that very much mixes the compute bound and the memory bound workloads with the different ratios. So this is the ratio 1:9, where 90% of the workload is a compute bound, which means that I see that the minimal energy savings are on the highest uncore frequency, and you see that on the highest core frequency. I'm sorry, and the uncore frequency is depicted by the colors of the lines. So you see that the low frequency is the low uncore frequency are optimal here. So as I progress, so I increase the memory bound workload, then you see that the application, the optimal setting is changing, and the optimal point is moving to the lower core frequency and to the higher frequency. So if I go to the other side of the spectrum, I see that my optimal core frequency is 1.6, and my optimal uncore frequency is a 2.8. So this should show you how the different arithmetic intensity change the behavior of the CPU, and the different tuning is important for different regions, because usually different regions have different arithmetic intensity. So in these slides, I would like to show what is the difference actually if you perform the the dynamic and the static tuning. So right now I have just a one-to-one ratio of a compute and memory bound workload, which is the low CI means low computational intensity, high CI mean high computational intensity. So I have two kernels. One of them is a compute bound, which is the graph in the middle. One is a memory bound, which is the graph on the left. And I see that my optimas are here. And again, you see that for compute bound, high core frequency, for memory bound, low core frequency, and appropriate the uncore frequency. But if I run this workload, if I analyze this workload as a 1, the graphs would looks like that. So I see that my optimal settings is a 2.4, which the core frequency is 2.4, which plays in favor of the compute bound workload, but doesn't play in favor of the memory bound workload at all. So this is the difference. If you perform the static tuning, you would select this point, and for this point, your energy savings would be approximately 9%. On the other hand, if you have a dynamic tuning and you select for one region the optimal point for that particular region, and for the compute bound region you select this point, then you're getting additional 12% of the savings. So this is the key difference. This is like what is the key difference between static and dynamic tuning, and where actually the savings comes from. So another important topic is if your system is running under the power cap, and you need to find the optimal settings under the certain power cap. So we've designed a set of experiments that pretty much compared the default behavior of the CPU, which is the experiment number 0, which is kind of a baseline, with the default CPU behavior under the power cap, and then we perform the core frequency tuning, uncore frequency tuning, then the combination of the core and uncore frequency with and without the power cap. So pretty much this is just all the combination. If you have power capping, the DVFS in this case is a CPU core frequency and uncore CPU frequency. We run this test on the processor that has 145 TDP, and it's an Intel Broadwell processor. And what we've seen is that the processor for certain types of workload doesn't have to run on such high power consumption to get the optimal performance. And this is what I'm going to show you on the upcoming slides. So we pretty much run the experiments on 3 different power cap levels. So the default behavior, it's 145 watts, that's no power cap. And then we run the application on the 100, 80, and 60 watt power cap levels. So first of all, we run it for a compute bound workload. So if we look at this slide, the default configuration is always this line, and this is kind of the baseline. This is what we compare against. And on the top, the set of lines on the top is the energy, and the set of lines on the bottom is a runtime. And the different experiments, which is also described in the legend, is shown here. So this is the idea of this is the example when we're running a compute bound workload on a 100 watt power cap. But pretty much we can see that again against the default value, if it comes to a runtime, we can pretty much, by underclocking the uncore frequency, which is this blue line going from right to left, by lowering the uncore frequency, we have more power that can go to the core region of the CPU, and then we pretty much eliminate the penalty of the power cap and just give the cores of the CPU enough power to run on the optimal settings. And further, we can also perform, just if we find the optimal settings of the core and uncore, we can also save some energy. So in this case, for the optimal settings running this, the compute bound workload, which by the way, in this case was a matrix multiplication from the MKL library, you can save up to 15% of the energy, and you can also save 4.5% of the runtime. If we go a little bit further, so we set the power cap to the 80 watts, we see that by reducing the encore frequency and pretty much shifting the energy from the encore part to the core part, we are not able to fully eliminate the slowdown given by the power cap, but we can still recover the up to 8.5% of the performance. This is pretty much going from here to here. I'm sorry, going from here to here. This 3.2 is the baseline. So, but under the power cap, if we just set the power cap, then the performance, then the kernel runtime would be 3.9 seconds. If we perform the tuning, then we get 8% extra of we reduce the runtime by 8%. And in addition to that, if we look on the same configuration, we save additional 8% of the energy. If we go a little bit further to the 60 watt power cap, again, the situation is pretty much similar. We can recover some of the performance, and we save some of the energy. In this case, it's a 9% of the energy saving and 9% of the time saving. But we are not able to really achieve the full performance. You see that for the compute bound and the 60 watt, the processor simply doesn't have enough power to run at the full scale. But what is the key message from this is that if you doing the tuning under the power cap, then you can save both time and the energy. And now let's take a look at the memory bound workloads, which are actually more often in real world applications. So let's start again with the 100 watts experiment, and we can see that we have, let's say, I have denoted like two options. We can, for the compute bound workload, we can save up to 40% of the energy, but at the cost of, let's say, 3.6 runtime penalty. And we can pretty much just maintain the optimal performance. If we set the power cap to the 80%, we can save a little bit less energy, because some of the energy savings have been actually achieved by setting up the power cap. But so again, we save 21% of the energy, and we extend the runtime by 3.6 seconds. But the most important part that I would like to present is that if you are running a memory bound workload under the 60 watt power cap, you can actually pretty much almost recover the runtime that you would have at the full TDP. So this is the figure here. So if this is the 1.92, this dashed line is the optimal performance. I'm sorry, this is 1.88, and then this 2.475, it's pretty much the runtime under the power cap, and the red line or the black dot line is pretty much if you underclock your core frequency, which is the red line. If you underclock your clock frequency you just move the power from the cores to the uncore region. And while uncore region is not as power hungry as a CPU cores, you can pretty much recover almost the entire performance of the CPU while running on the full TDP. In this case, we were able to recover 22% of the runtime, but you see it's only 5% slower than if the CPU would run on the TDP. So for the memory bound workload, both performance and the energy savings can be very high because the power is shifted correctly from the cores to the uncore part. The uncore part can run faster and can get the data from the memory more efficiently, and then the processing simply runs faster. So if we kind of if we summarize what we've seen on the slides, we can see that under the power budget lower than 80%, we have that 60% example. The boost performance can be up to 22%. We can recover a significant part of the performance by just shifting the power from cores to the uncore part of the region. For the compute bound workloads, we can again for higher power gaps, let's say 100 watts, we can recover a significant part of the performance and also save some of the energy, as I showed on the previous slide. So this was pretty much the key ideas behind what can be achieved by the tuning under the certain situations. And right now I'm just going to show several applications that achieved like significant savings, and to give you the idea where the savings actually comes from. So this is the BEM4i application, and the BEM4i is pretty much a boundary element method which has 4 significant regions. So it has the assemble K, assemble V that assembles the matrices. It has a solve, which is iterative GMRS solver, and then it has a print VTU region that pretty much saves the results to the file. So we have 2 regions that are compute bound. Actually, they are very efficiently vectorized. They really are optimized to the core and take a full advantage of the AVX units. Then the GMRS solve is a GMRS solve from where pretty much the key application is the key kernel is dense matrix vector multiplication. So this is a memory bound core, and then we have a print VTU, which is IO bound region that saves the data to the hard drive. And so we see that for these regions on the right side, we see that we have following optimal settings. The assemble K, assemble V, they need a high core frequency, full number of threads, and lower uncore frequency, while the GMRS solves needs a lower core frequency. It needs a lower number of threads and a higher uncore frequency. And the VTU, the IO bound, requires the higher core frequency, low number of threads, and uncore frequency of 2.4 gigahertz. I'm sorry, the 23 here means 2.3 in terms of the frequency. So these are the optimal. These are the regions that we have, and so if right now we are looking how the runtime is affected by the tuning. So if I find the static optimal settings for the entire applications that maximizes the energy savings, then in terms of the runtime, I'm losing up to 80% of the runtime in the assemble regions, and I'm gaining 40 and 56% in the GMRS solve and the print VTU regions. So clearly the GMRS solve and the print VTU are the dominant regions in the applications, while the assemble K and assemble V pretty much have to follow the optimal settings set by these two regions. If I find the optimal settings for each of the regions, I'm gaining the dynamic savings are the penalty in terms of runtime is slower. If I look at the runtime, I'm sorry. If I look at the energy savings, I can see that I can gain up to, I have no loss in, I have very small amount of saving in assemble K and assemble V, because usually the CPU runs on against the default, it runs on the normal frequency, so there is not much to gain for this. But I have 53% and 74% of the savings for the GMRS solve and the print VTU in terms of the energy. So this pretty much tells me that on average I can save up to 34% of the energy, while in this case my runtime would be improved by 10% as well. So this is the evaluation of the OpenFOAM. So pretty much for the OpenFOAM, we show that the energy savings can be, by static tuning, can be up to 15 and 16%. Then additional 5% can be achieved from the dynamic tuning, and it's pretty much these are the regions of the OpenFOAM that has been used for the runtime for the particular benchmark. The orange ones are the ones that are significant regions and that we actually tune, and the tuning for this particular region is shown in this figure, but I don't think we have to go into such detail. Just this is how the OpenFOAM was pretty much annotated what were the significant regions. The last complex application that has been thoroughly evaluated was the ESPRESO. So the ESPRESO is a finite element application and the solver. So it uses it's a finite element assembler. So it assembles the matrices. It solves the problem using fetish solver and store the results to data. In this case, we pretty much focus on the assembler and on the solver, because the saving of the results was negligible. In this time, we didn't store the entire mesh, just a set of results. So, but what this table is showing it that it actually shows how the saving evolves when you scale the application. So this is a strong scaling of a problem, and we see that if we have one node, that the energy savings can be up to 8%, and we pay the savings very much by the extension of a runtime. But as we further scale the application, I'm repeating, this is a strong scaling, so we pretty much change the workload per core, because we are solving smaller and smaller problem. The problem, more and more of the data fits into the caches. Sometimes it's at certain point it's not efficient to utilize all the cores, etc. So while performing the scaling, we see that the energy savings are improving, and on the other hand, the runtime penalty is pretty much reduced. Even at first we pay the penalty up to 11% of the runtime, and at the end we actually do save up to 22% of a runtime when running on 128 nodes. So in this case, I mean, the tuning here both improved the scalability of the applications, as well as the the energy consumptions. The figure on the right just shows all the regions that have been used and that have been tuned. So all the gray regions have been tuned, and all the white regions have not been. So all these gray regions have been tuned. So the last part is the application tuning. So again, the motivation behind this work is that I mean, if you use some third-party software, you might not be aware of what is the optimal configuration of that particular software to solve your problem. These are like the application parameters. So this is example of the ESPRESO, just one part of it, which is the FETI solver. So we have the FETI solver, we have like 9 key parameters, and it has up to 4,000 of the combinations. And different, I mean, you can set the parameters the way you want, but it significantly affects the runtime and the energy consumptions. So this graph is just, we took our time and ran all the configurations to see what is the variation if you have optimal and non-optimal settings. And then we talked to the expert that is using such a software, and he said what he would know by his experience, what would be the optimal settings. That's pretty much is the line that's called the reasonable settings. And something underneath is that what we found that there are configurations where the solver behaves better than that. So for some applications, this is worth of actually running such experiments and search the space for the optimal configuration of the application parameters. So this was just very extensive, but we perform it on other tools. We tried on the Elmer, we tried on the OpenFOAM and on the Indeed. But the idea is that there is a software that can pretty much perform this search for you if you're interested, and it can find the optimal configuration, which has also can have significant impact on the performance of your software. So thank you very much. This is the end of my talk, and let's see if there are any questions. So there is a question: how can I apply these techniques on my university HPC cluster where I don't have root elevated privileges? So pretty much there are tools like MSR Safe that we use and that we rely on, that allows you to change the core and the uncore frequencies, and potentially also measure the energy consumption using the RAPL counters, even if you are not, if you don't have the administrative privileges. You just need to talk to your administrators who will install the MSR Safe for you, and they will allow you to tune just these particular knobs of your systems. This is the approach that we use on our HPC systems at IT4I. So we have talked to our administrators. We said we need these knobs to be accessible to us, and they have installed the MSR Safe, and we are able to do that. So yes, you can be a user, and with this tool you can do the tuning. The other question: will use of a GPU HPC in geological imaging improve the energy efficiency of HPC? I mean, so GPUs on average are more efficient than the CPUs if your code is optimal. So as long as you can achieve a speed up of certain speed up, and you are able to utilize the GPUs efficiently, then the GPUs on average will give you higher energy efficiency of that. And we also, as of now, we are working on performing the dynamic tuning also for the GPU. So this is our current work. So this potentially can further improve the energy efficiency of the GPU. But on average, yes, the GPU are considered to be the more energy efficient platform, and moving your code to the GPU has a high potential of saving the energy. So there's a question, do you plan to run the same tests on CPU architectures, PowerPC, ARM? So there's a slight problem we've run these tests on a Davide system in Cineca, which is a Power 8 processor, and that allowed us to tune the core frequency, the number of threads. There was no knob on the uncore frequency. So the test can be run on a different architectures. I mean, it's very much our application, the library that we use for the tuning that can be compiled for the ARM, for the PowerPC. It always depends whether the architecture has the correct knobs to perform the tuning. In the slide on the arithmetic intensity, oh, I'm sorry. So this is the question is about this. So the arithmetic intensity is pretty much show how many operations you perform per byte that you read from the data memory to from the DRAM to the processor. So so if you have a memory bound workloads like sparse blast, tensor, lattice Boltzmann methods, you perform let's say 0.1 up to 1 operations per byte. If you have a compute bound applications, you pretty much perform like tens of operations per every byte that you read. Then the questions, are you aware of any usage of dynamic tuning for HPDA applications? Within the project, we mostly focus on the HPC applications that use the OpenMP for the threading. But on average, on general, you can any application, even single core or the MPI without the OpenMP, you still have potential to tune the core and the uncore frequency, and that's really independent on any. It doesn't have to be HPC, but we don't have any results for the HPC application as of now. So the question, how do you calculate the arithmetic intensity operations? So usually we used to calculate the arithmetic. If we measure the arithmetic intensity, if you want to measure it, you just you can calculate the number of last level cache misses and the number of floating point operations that your cores perform together. And second part of the question is for BEM4i, how do you get the optimal configuration? Do you measure all the configurations? Yes, within the project, we wanted to measure all the configurations. So we did the brute force search, but since then in our software, which implements the methodology of the READEX, but it's not the READEX tool suite. But that software has already some advanced methods to search the space. But pretty much, yes, I mean, you have to search the space to find the optimal settings, and you can use different space search strategies to do that. Okay, so this is we get to the end of the webinar. Thank you very much for your attention. And if you have any questions, and more importantly, if you interested in having such analysis to done on your application, please apply to POP, and we will be very happy to do that for you.